All right, so we are going to get into kind of the whole reason why we were talking about Newman projections and knowing how to draw them, because we're going to be looking at how um, a compound can adopt different conformations and therefore have different stabilities depending on the orientation of that conformation. And we're going to be using Newman projections to help visualize those as well as kind of show why these molecules, the conformations are not equal in energy. So we're going to start off very basic by looking at ethane. So this is just ethane molecule. These are all hydrogens on here on each carbon. I'm just highlighting these specifically because I might point some things out. That's why they're a slightly different color. But I'm going to turn this way. And what you'll notice is that I can rotate around a single bond, a carbon-carbon single bond here. And each part where I stop, I can stop here or here or here or here, basically kind of infinite as we go around the circle. We call that a conformation. And we don't care about all of them. We only care generally about a few types of conformations as we rotate around that single bond. Now, one of the ones that we care about is when all of the hydrogens in the front are aligned with the hydrogens in the back. And we call that the eclipsed conformation. One thing to note is that this is the closest the hydrogens in the front will be to the ones in the back. All right, now I want you to keep that in mind, especially when it comes to stability. Now, you will notice that these hydrogens, the red ones, are completely in line with each other. We call that, we say that that has a dihedral angle of 0 degrees. Now, if we're going to write the Newman projection for this, exactly what you see here. So we'll do our circle and a peace sign. Again, the peace sign in front represents the front carbon. So we have hydrogen, hydrogen, and hydrogen. And actually, what I'll do is I'll make this one red to match the um, actual model here. And then to show they are eclipsed, we'll have hydrogen, hydrogen, and hydrogen. And this is called the eclipsed conformation. Now, as I rotate this back carbon here, notice the hydrogens, the red ones, are getting farther and farther apart until I get to this conformation right here. This is as far as the hydrogens in the front will be in the hydrogens in the back. Because eventually, if I keep on going, then I'm going back to another eclipsed conformation. So let me go back to this one and just kind of point out. So at this point, we call this the staggered conformation. So let's draw that, a new projection for that. So again, I'm just highlighting the red ones here just so that we can keep track of them. But they're all essentially the same. All the hydrogens are exactly the same. And we call that a staggered conformation. Now, because the hydrogens in the front are as far away as they'll ever get from the hydrogens in the back, this is the most stable conformation or conformer of, of ethane. And so, again, just to equate that with energy, it has the least amount of energy. And that's good, especially in molecules. Molecules don't want to have a whole lot of energy because low energy equals high stability. And when the hydrogens here are in the front, are in line with each other, they're as close as they're ever going to get to each other. And so this is the least stable conformer of ethane. So it will have the most energy. Now, as I said before, this dihedral angle here is 0 degrees. And the dihedral angle of the hydrogens here in the staggered position is a 60-degree dihedral angle. Now, one of the things I want to emphasize is that all of the eclipsed conformations are what we say degenerate, meaning they're all equal in energy. If you look at the energy diagram to the right here, Notice all of the eclipsed conformations are equal in energy, and all of the staggered conformations are equal in energy. Now, the other important thing I want to point out numerically is the difference in energy between the staggered conformations and the eclipsed conformations. Notice the staggered here, if we kind of make that quote unquote zero, like our baseline, this is our baseline, it takes 12 kilojoules of energy to rotate to an eclipsed conformation. So we start here at a staggered, we have to supply 12 kilojoules of energy per mole to get this to rotate to an eclipse conformation. That is called torsional strain. So the energy required to go from staggered to eclipsed is called torsional strain. That's an important term. We're going to talk about a few different types of strain um, in um, in these conformations. So torsional strain just deals with rotating the bond. What does it take to get staggered to go from eclipsed? At room temperature, that happens without any problem. This bond is constantly rotating at room temperatures. Even cold temperatures, you got to get very, very, very cold to get that bond to stop rotating. But if you had like 100 molecules of ethane and you were able to take a picture of them at any point in time, most of them would be in a staggered conformation because that's the most stable, the least amount of energy. Now, if there are in the eclipsed 3 sets of eclipsing hydrogens, so 1, 2, and 3, if the total amount of torsional strain is 12 kilojoules per mole, then an eclipsing two eclipsing hydrogens would have a value of 4 kilojoules per mole. That's an important number. Keep that in the back of your mind because when we start adding groups other than hydrogens here, we're going to be able to add up the total torsional energy for a molecule. And knowing that eclipsing hydrogens is 4, that's an important value. Now let's get a little bit more complicated, not really complicated, but more complex. And let's go into propane. So all I did was add another carbon, and we're going to look right down this carbon. This is going to become our Newman projection. Okay. Now notice all I really did was I took a hydrogen off the back here and replaced it with a carbon. And so the same concepts are going to start to apply to propane as they did with ethane. I'm just going, when notice I rotate around this bond, this stagger conformation puts the atoms in the front as far as they're ever going to be in the atoms in the back. And just like this eclipsed conformation, if these are all hydrogens, this eclipsed conformation is exactly the same as this one, as it is to this one. Okay, so let's draw this eclipsed conformation. And then I recommend that you get some practice with Newman projections and draw the other ones. So we'll start here. And so this eclipsed conformation, there's hydrogens in the front. And then in the back, so there's this methyl group right here, and H and H. Now, let's find the total torsional energy that occurs when you have 2 sets of eclipsing hydrogens and a hydrogen eclipsing with the methyl group. Okay, we already said in the previous page that eclipsing hydrogens supply 4 kilojoules per mole of energy. So because methyl is a little bit bigger, that is going to supply more energy. In fact, the value for that is 6 kilojoules per mole. So The eclipsed conformation is a total of 14 kilojoules per mole less stable than a staggered conformation. All right, so let's draw a staggered conformation for this. So I'm just rotating the carbon in the back. So the front stays put, all these are still hydrogen. And then all I did was rotate the carbon in the back. This was eclipsed, and now this is staggered. And just like before, the staggered conformation is more stable than any of the eclipsed conformation. And like ethane, I want you to note that all of the eclipsed conformers are equal in energy, they're degenerate, and all of the staggered conformers are equal in energy. Okay, so really propane and ethane are pretty much the same in terms of that respect. The only difference is the difference in energy between the staggered and eclipsed. So again, that 14 kilojoules per mole represents the torsional strain of forcing staggered propane to rotate into eclipsed propane. All right, now let's add one more layer of complexity and look at butane. So I'm going to put one more carbon on here. Okay. And so again, let's just kind of start off. Here's butane, 4 carbons. And what we're going to do is I'm just going to turn this around and we're going to look at it like it were a Newman projection. Now, butane is going to start to incorporate a new type of strain because I have two massive groups on the end here. Anything bigger than hydrogen and they're on adjacent carbons is going to cause something called steric strain. So I'm going to turn butane again this way. And I want you to imagine the model kit kind of separates them, but these methyl groups are so close together, they're kind of within each other's van der Waals radii. And what that does is that puts electrons close to electrons, which they don't like that. So that is something that we call steric strain. So steric strain occurs when atoms or groups of atoms are closer than what their van der Waals radii, I can't remember how to spell radii. I think it's just two I's, allow. So I'm going to kind of slowly rotate around through like 360 degrees around. And I want you to note a few things. I want you to start to note, are there any places where the eclipse conformations are the same or different in energy? Are there any places where the staggered conformations are the same or equal in energy? So I'm starting in this eclipsed conformations. Notice the methyl group, the methyl groups here are as close as they are ever going to get. Now I'm going to rotate to our first staggered conformation. Okay. Notice where the two methyl groups are. Now I'm going to rotate to this staggered conformation. Actually, I'm sorry, this eclipsed. Okay. So hydrogen in line with the methyl in line with the hydrogen, methyl in line with the hydrogen, and then two hydrogens over here. Then I'm going to go to this staggered conformation. Look how far apart this methyl is from this one. Back that up a little bit. There we go. This methyl group compared to this one. That's a bigger distance. So would you say that this staggered conformation is different in energy with this one? So answer that question in your head before I answer it aloud. Since these methyl groups are as far away as they're ever going to get, there's no steric strain there. So this staggered conformation is actually more stable, that's energy, than this staggered conformation. That's something new. We did not see that with ethane or propane. I'm going to go back here. And then I'm going to go to this eclipsed conformation. And finally, this staggered one. And then we're back to the original eclipsed. Okay, so let's start at that eclipsed conformation at the very beginning, where the methyl groups are as close as they're ever going to get. So that's what that eclipsed conformation is going to look like. Now I'm gonna do all the eclipsed ones. So I'm gonna just rotate around and get to the next one. So now the methyl group in the back is eclipsing with a hydrogen. This is slightly more stable than this one. Why is that? Because instead of having two big methyl groups eclipsing, it's now just methyl and hydrogen. Okay, now let's actually, I think I forgot some things here. Yes, I forgot to put the hydrogen right there. Sorry. So let's actually look at this in terms of numbers. Okay, so we have two eclipsing hydrogens here. So those are both 4 and 4. Now, the value for two eclipsing methyl groups is super high because of that steric strain. So if we add all of that up for that first first eclipse conformation, that's a value of 19 kilojoules per mole. Now, if we do the math for these other ones, this is 4. We just saw on the previous page, this is 6, and this one is 6. That's a total of only 16 kilojoules per mole. So these two eclipsing conformations, draw the opposite one here. These are both equal in energy, but less than the first one. In fact, if we look at the energy diagram and just look at the eclipsing interactions, notice that these two are degenerate, but this one, where the methyl groups are completely in line with each other, is higher in energy. Now, let's go to the stagger conformations. And I'm going to start with the one where the methyl groups are as far apart as they're ever going to be. So we'll have one methyl up and one methyl down. They're never going to get any farther apart. And because of that, we give this stagger conformation a special name. We call it the anti-conformation. And it is the most stable conformer of butane. Now, as I rotate, I'm going to rotate that back carbon to one of the other staggered conformations. I'm kind of forcing those methyl groups to get closer. So what I did here, I'm going to rotate this one in the back to go this direction now. Still staggered, but I'm increasing the steric strain because I'm getting those methyl groups closer. Since it's still staggered, but we give it a special name of the gauche conformation. And I'm going to draw the other one, the other staggered conformation. This one's also called the gauche conformation. And if you look at those two, they are both equal in energy, and slightly less stable. Oh, I should probably put it this way. Greater in energy than the anti-conformation. So let's look at the energy diagram here. And let's compare the anti, this one right here, to the gauche conformations, these two here. Notice the gauche conformations are equal in energy, but a little less stable than the anti-conformation. That value that we assign, that gauche interaction between two methyl groups is 3.8 kilojoules per mole. All right, so we're going to work on some problems just to solidify this conformation stuff. Now, here's a great table from one of the textbooks that kind of summarize the types of strain that we've talked about as well as their energy cost. I would know these numbers. I don't say to memorize numbers a whole lot, but I might ask a question on an exam, like showing a conformation, and you should be able to, with these numbers, predict what the total energy of a conformation is. Okay, so we are going to look at this compound and identify the lowest and highest energy conformation. So we're basically, I'm going to number these here. We're going to look down at number 3 carbon. So number 3 will be the front carbon in our Newman projection, and number 4 will be the carbon in the back. Okay, so let's draw the front carbon, carbon number 3. So we'll start with, so that group is going up. Oops. And so the group that's going up will be this ethyl group. And then the group with the solid wedge, this methyl, will be going out to the right. So I'm going to put that there. And then the hydrogen will be going to the left. Now, what does carbon number 4, the rear carbon, look like? Well, all it has, drawn specifically, is going downward, carbon 5 and 6. And then it'll have the hydrogens. So now, just like we've done in the past, I'm going to put those two together. So there's my front carbon. There's the rear carbon. And now that's a Newman projection, but let's answer the questions here. Lowest and highest energy. Did I inadvertently draw one of those, the lowest or the highest energy? Now, in a problem like this, where we have like two different types of groups, we have an ethyl and a methyl in the front, and then we got an ethyl in the back. How do I know what, is the highest and the lowest? So I'm going to draw the other conformations. I'm going to rotate the back carbon here. So I'm going to draw the other staggered conformations. So keep that one in the same. Okay, so notice now where the two ethyls are. I got an ethyl here and an ethyl here. And then I'm going to draw the other staggered conformation. So there's the ethyl in the front and the ethyl in the back. Now, why am I focusing on the ethyls? Okay, try to answer that question in your head. I'm focusing on the ethyl groups because they're the biggest groups in the front and the rear carbon. And if I have to keep those two apart I want to try to keep those two as far apart as I can. So if I look at where those ethyl groups are, this one here puts them the farthest apart that they're ever going to be. That's going to be my lowest energy conformation. What kind of conformation should I show if I want the absolute highest energy conformation? Well, I know number one, that that would have to be an eclipsed. And number two, it would have to be the putting the biggest groups on the front and rear carbons in line with each other. So I'm going to do that now. I'm going to rotate so that the ethyl groups are eclipsing. So the biggest group in the front is eclipsing with the biggest group in the back. And that's going to be my least stable conformation. Yeah, I'd recommend, get some practice with drawing the other eclipsed conformations. But two ethyl groups, because they're so big, is a much bigger steric strain if they're eclipsing than, say, a methyl with an ethyl. All right, so this next one is asking us to predict the energy barrier when we rotate 2,2-dimethyl propane. They're actually wanting the energy values there. Okay, well, let's just start off by drawing 2,2-dimethyl propane. And we're going to look down this bond right here. So that's us. We're all looking down that bond. And we're going to draw a Newman projection for that. Now our front carbon, it's like, why aren't you drawing dashes or wedges? Well, they're all the same group. They're all CH3s. And then the rear carbon, that guy right there, is just all hydrogens. Oops. Okay, so let's draw a staggered conformation. So I have three CH3s in the front and three hydrogens in the back. Now, in order to figure out the barrier to rotation, that's my most stable conformation. And I'm going to rotate the carbon in the back. Oops. To make an eclipsed conformation. Now, how much energy is this going to cost to go from here? I'm sorry, yeah, from staggered to eclipsed. Well, I just got to add up what the eclipsing interactions are. A CH3 eclipsing with a hydrogen, go back to our table, go back to the problems we've done, requires 6 kilojoules per mole. And I have 3 of them. So the barrier to rotation is going to be 18 kilojoules per mole. All right, let's take a look now and expand this to this concept of conformation to rings. And I'm going to breeze through a few of the types of cycloalkanes and spend basically the rest of the chapter on one cycloalkane in particular. So when we start incorporating rings in our conformation discussion, we're going to add one more type of strain. And that strain that we're going to look at is called angle strain. This is an increase in energy associated with a bond angle that has deviated from 109.5 degrees. So if we're talking about sp3 hybridized carbons in a ring, we know the bond angle should be about 109. When we put those into a ring, sometimes we cause those bond angles to be less than that, and that creates strain because you're kind of, well, I'll show you here in a little bit. Let's look at cyclopropane, and I'll show you with the model kit. When I draw the skeleton formula for cyclopropane, it's a triangle. Okay, so remember your geometry. What are the bond angles in that triangle? Or I should say, what's the angle of all three angles of that triangle? It's 60 degrees. So if I start with regular propane, kind of notice what I have to do with my model kit to get to cyclopropane. Notice how those bonds are like bending like that and almost breaking practically. Okay. So notice kind of how weird my bonds look on my model. I'm forcing something that likes to be 109 to be 60 degrees. Now, here's the other thing I want to show you. I want to turn this and I want you to look at it like it were a Newman projection. What do you see about the hydrogens in the front and the hydrogens in the back? They're all eclipsing. So you have all of these eclipsing interactions in cyclopropane. So here's how we would draw that Newman projection. It's going to look a little weird, but you should get used to seeing and drawing Newman projections for rings. And all the groups are eclipsed. So you got a lot of ring strain, you got all these eclipsing interactions, and so cyclopropane, very, very, very unstable. In fact, I kind of encourage you if you are looking up, maybe look up some structures of biomolecules. You will see that most organic molecules that exist in nature, if they have a ring, it's going to be either a five-membered ring or a six-membered ring because those are the most stable rings. It's very rare to see a four-membered ring, and you probably would never see a naturally occurring compound have a three-membered ring. It'd be very, very rare. Now let's go to cyclobutane. So we use a square to represent the skeleton formula. And what are the angles of a square? They're all 90 degrees. Again, that's a lot less than 109. Now, here's something that cyclobutane can do that cyclopropane can't. So I'm going to build a model here. If I try to put cyclobutane flat, notice it has eclipsing interactions as well. So when you're looking, say, look down this carbon like a Newman projection, you'll see that everything is eclipsing. What cyclobutane can do is it can rotate one of the carbons out of the plane. It creates a little bit more ring strain. So the actual bond angle of cyclobutane is about like 88 degrees. So here's how we would, draw this structure. Again, it's going to look a little weird. I'll draw the hydrogens in here. And the bond angle is about 88 degrees. So what it does is it increases the angle strain just a little bit. But no more eclipsing hydrogens. It's like the ends justify the means because cyclobutane ends up being more stable in this non-planar form. Try to see if you kind of see how it's kind of curved a little bit. Instead of it being flat, there's no longer any eclipsing hydrogens here. actually almost like to the point where they're staggered. And so that's a lot better for cyclobutane. And then finally, let's look at a five-membered ring, cyclopentane. Now we're kind of getting into almost normal. So build cyclopentane here. Now, if we were to draw the skeleton formula for cyclopentane, we just use a pentagon. But if I were to try to make cyclopentane flat, what do you notice as you look down this carbon right here, like a Newman projection? You have eclipsing hydrogens. So cyclopentane, like cyclobutane, will sacrifice a little bit of angle strain and take one of the carbons and move it out of the plane. And notice now the hydrogens are no longer eclipsing. So you have this, what's called an envelope conformation. And that means no eclipsing hydrogens. So again, sacrifices a little angle strain, but in the end, it's much more stable because it got rid of all the eclipsing hydrogens. And I forgot to mention this, but with cyclobutane, this is called the butterfly conformation. Not sure why. Maybe it does look like a butterfly. I can't really tell, but that's what they called that conformation. Now that will pretty much conclude it for this lecture. I'm going to spend a lot of time in the next one talking about cyclohexane because there's a couple of conformations that we're going to highlight. And there's a lot of things that happen with cyclohexane when we put groups on it that doesn't happen with any other ring. So we will continue that on the next lecture.